Hello everyone and welcome back to my YouTube channel. Today we are going to learn the slope, deflection and bending moment when beam is acting a point load at the center. In last lecture we already seen what is the relation between the deflection, slope, bending moment, shear force and rate of loading. So I am sharing this screen over here to get the idea about what is the relation between the deflection, slope and bending moment. Here if you observe the bending moment formula, if you take the integration then we will get the slope, and if you take again integration then we will get the deflection. Same phenomena we will use to solve when a simply supported beam is at a point load. Clear? So I hope it will be an interesting lecture. So please bear with me. So let's say this is beam A and B having a point load at the center. So let's say the point load is W. Now as we seen, the entire length of the beam is L. So here I will consider L by 2 and L by 2. The point at which at center where the load is acting, that point is C. Now when the load is act on the body on the simply supported beam, the body will tends to bend. So try to understand, this will be the bending of the beam. Simple. Now if you observe at the center, it will be a maximum deflection, and if you consider the slope over here, so we will find the slope at different point. So if you consider slope for this particular beam, then I can draw a tangent. So this angle is nothing but it's a theta. So if you ask me, sir, what it will be the slope at this center, definitely slope will be 0. Simple. Now what is happening over here? A load is applied and the simply supported beam, it went for the deflection. Now let's start the problem. When the force is acting and as it is simply supported, then definitely there will be a two reaction force will be there. So I will write RA and RB. As we learn how to find out the shear force and bending moment, then I can say that definitely if the load, a single load is acting at the center, then definitely RA value will be W by 2 and RB will be W by 2. It's very easy. You can take moment also, or summation of f of x is equal to 0 or and f of y equal to 0, and if you take the moment, so in this case if you take summation of f of y equal to 0 and moment, you will get the value of RA and RB. Simple. Now what I will do, I will consider one section. Clear? So here I will consider one section. I will name it as XX, and I will consider the section at a distance of x from the point A. Clear? Now when I consider the section, then I will write the moment at section, and it will be RA into X. Simple. Now here I am considering the forces acting on left side of the section. So as it is a clockwise, I am considering it positive. Simple. Now I will write the value for RA, W by 2 into X. So this is the movement at section XX. Simple. Now in previous video we have already learned the bending moment. It can be evaluated through this formula. So at any section, if you want to evaluate the bending moment, then the formula is bending moment M it will be equal to ei into d2y divided by dx square. Simple. Now here I will consider this is equation 1 and equation 2. Now if you compare these two equations, then I will write ei into d2y divided by dx square equal to w by 2 into x. Simple. So this is an bending moment equation. As we already discussed, if you take integration of this bending moment equation, we will get the slope equation. So what I will do, on integrating, on integration we get, so here ei it is constant, then integration of d2y divided by dx square, you know, dy by dx equal to w by 2, it's a point load and it's a constant, x square, integration of x is x square divided by 2 plus c1. Now what is c1? C1 is constant, integration constant. Simple. Okay, so here we get the new equation. So here I can say third number, equation number third. Now in this equation what I will do, I will put the boundary condition. So by applying boundary condition. So what are the boundary condition? So let's say at center means when x is equal to L by 2, what I already told you that slope will be 0. Simple. So that means dy by dx, it is nothing but slope, it will be 0. Simple. Just put these values in equation number 3. Okay, so here ei into 0 equal to w by 2 into L by 2 whole square plus c1. Simple. So anything multiplied by 0, it will be 0. So 0 equal to w L square, 2 square is 4, 4 into 2, 8. Simple. Okay. Simple. Okay, let me check. Here if you observe, it's 2 and this is 2. It will become 4 over here. So it says 16. That's why I'm thinking why this happened. So 2 multiplied by 2, it will become w by 4. And instead of x, I am writing L by 2 whole square. Clear? So this will be the C1. So value for C1, it will be equal to minus WL square divided by 16. Simple. By substituting these values in equation number 1, so from equation 1, by putting C1 value, I will get equation ei dy by dx equal to wx square divided by 2. Now again it will be wx divided by 4. Am I right? Yes. Ei into wl square by 4, and the value is of C1 is wl square divided by 16. Simple. So this is the equation of slope. So we can say this is the equation of slope. Simple. So we can find a slope anywhere. Clear? So at any distance of x we can find out, but from 0 to x, 0 to L value. That's it. Now let's evaluate slope at point A. Now at point A means when x is equal to 0. So just put these values in this equation. So let's say this is 4 equation. So I can say from equation number 4 I can write ei dy by dx at a equal to w into 0 by 4 minus wl square divided by 16. So here I can write ei. So I will write theta a equal to minus wl square divided by 16. So this will become 0. Simple. So if I take ei that's in that side, then I can say theta a, or we can say slope at a, that will be equal to wl square divided by 16 ei. Simple. Now if you observe here, I will get the slope at a minus wl square divided by minus 16 ei. Clear? But remember the theta a, it will be in radian. So that is very important. Simple. If in degree is given, convert it into radian and then evaluate. Simple. Now this is all about the slope. Then how to get deflection then? Again take integration. Simple. So what we will do? We will integrate the equation, slope equation. So I will tell you. So this equation is there. Clear? So you need to take the integration of this equation. So integrating slope. So I will directly write here integrating slope equation. We will get e into I into y equal to w by 4 into x square. Integration of x square is x cube divided by 3 minus wl square divided by 16. It's a constant. So into x plus here I will get c2. So this will be the equation number 4. Now just put the boundary condition as at a, or we can say x is equal to 0, y it will be 0. Simple. So if you just observe the diagram, if you observe at a y will be 0, at c y equal to yc, and at b y equal to again 0. Simple. So at a I am considering when x is 0, y will be equal to 0. Simple. I will just put the value of x and y here. So ei multiplied by 0 equal to w by 4 into 0 cube divided by 3 minus wl square divided by 16 into 0 plus c2. So anything multiplied by 0 it will become 0, anything multiplied by 0 it will become 0, and this will also become 0. So I can write directly c2 equal to the 0. Now just substitute this value in equation number 5. So put this value in equation number 5. Simple. So by putting the value I will get another equation, that is ei into y equal to w by 4 into x cube divided by 3 minus wl square divided by 16 into x. Simple. Now this above equation is known as the deflection equation. Simple. So where will be the maximum deflection? As we have seen, Deflection at A will be 0, deflection at B it will be 0, maximum deflection we will get at the center. So what we will do, we will evaluate the maximum deflection at center, means when x will be equal to L by 2. Just put all the value over here. EI into, instead of y I can write YC, W by 4 into, so here remember 4 into 3, so here I will multiply 3. Now instead of x I will write L by 2 cube minus x. So instead of x I will write L by 2. Clear? So I will again simplify this equation. YC equal to W into L cube divided by 96 minus WL square cube divided by 16 into 32. So here what I will do, I will take common 96, then WL cube minus 3 WL square, sorry again it is cube not square, cube. So this will remain same into YC. So EI into YC equal to 1 minus 3, it will be equal to minus 2 into WL cube divided by 96. If you just cut, then here I will get 48. Simple. Now equation will become EI into YC equal to minus WL cube divided by 48. And if I want deflection at the center, then I will transfer this EI in that direction, 48 EI. Simple. So this is an deflection, maximum deflection occur in simply supported beam when there is a point load at the center. Now you may observe over here the sign is negative. Why? Because it's in downward direction. Simple. So simply if I want to write downward maximum deflection at center, then I can write YC equal to WL cube divided by 48 EI. Simple. So this is all about the simply supported beam when the point load is acting. Likewise, if you derive the derivation for deflection of a simply supported beam with an eccentric point load. Simple. So if there is a beam is there, and if there is a eccentric load is acting on the beam, let's say this distance is A, this distance is B, and entire distance is L. At that time you will get slope at A, that will be, I will write directly, we can derive the equation, that will be the 6 EI into L A plus 2B. So slope at A. So maximum deflection at YC if you consider, then it will be equal to, sorry, equation at center, deflection at center, that it will be W into A square B square divided by 3 EI into L. And if you evaluate the maximum deflection, then it will be the W into L divided by 9 root 3 EI into L multiplied by A square plus 2AB 3 by 2. Simple. When the simply supported beam is acted with the eccentric point load. Simple. Likewise, if you evaluate deflection of a simply supported beam with a uniform distributed load. Clear? So at that time you will get the slope at A, that will be the minus WL square divided by 24 EI, and deflection at center, that will be equal to 5i 384 into WL cube divided by EI. Simple. Now here if you observe this W is nothing but it's a W into L, so this is nothing but it's a UDL. Clear? So we have converted that into the point load, or we can say total load. This is nothing but it's a total load. Likewise we can evaluate for the different conditions also. I hope you understood the derivation for a simply supported beam having a point load at the center. Clear? So based on that we will solve some numerical. Clear? I will read the numerical. What is given data? A beam 4 meter long is given, so L equal to 4 meter, so I will write in 4000 mm. Simply supported beam, its center carries a point load W at the center. There is a point load W is at the center. Slope at the end of beam is not exceed to end, so I can write 1 degree slope is there, so this is also called as dy by dx at A. However, it is given in degree, and what we will observe in our numerical derivation, that is in radian. So convert this 1 into radian. For that purpose multiply by pi by 180. So the value will be 0.01745 radian. Simple. So always consider slope in radian. Find the deflection at the center of beam. Clear? Now, so when we want to find out such problem, then what we will do? First we will use the deflection as it is given. Deflection of beam at A is given. So what I will do? I will use deflection at A. So what will the equation? WL square divided by 16 EI. 16 EI. Now the value is 0.01745. Clear? Now you may ask me, sir, nothing is given, W is not given, L is given, but E and I is not given. Don't worry, we don't require that value also. Why? Because we are going to use this equation, that is YC equal to WL cube divided by 48 EI. Simple. I know this value. Clear? WL square divided by EI. So what I will do? I will convert this equation in this form. So I will write WL square divided by 16 EI into, so what is remaining? 16 multiplied by 3, and here L cube is there, here I am writing L square, so I will write L by 3. Simple. Now it's very easy, so just put, instead of this I will use this equation value 0.01745 into value of L is 4000 divided by 3. So you will get the value of YC, it will be equal to 23.26 mm. Simple. Now why I am not using minus? Because I know the beam will deflect in downward direction only. Clear? So definitely maximum deflection will be the 23.26. Clear? So let's take another example. Now in this example, what is given data? Given data I will write first. A beam is 3 meter long. So So take it 6 meter long. So L equal to 6 meter, or we can say 6000 meter mm. Simply supported and carries a point load. So value of W is given, that is 50 kilo Newton. So I will convert it into the Newton. Moment of inertia is given 78. So I can say I, it is given 78 multiplied by 10 raised to 6 mm raised to 4. Now modulus of elasticity for the beam material is given, that is E equal to 2.1 into 10 raised to 5 Newton per mm square. Clear? Now what they are asking? They are asking deflection at the center. So directly I will use the formula YC, WL square divided by 48 EI. Clear? So here W is given 50,000 into L is given 6,000. So YC is there, so it's a cube divided by 48. Value of E is 2.1 into 10 raised to 5 into value of I is given 78 into 10 raised to 6. So YC value, it will be equal to 13.73 mm in downward direction only. Next, what they are asking? They are asking for the slope. So equation for the slope is theta A, or we can say for theta B, that will be equal to minus WL cube divided by 16 EI. So here I can write, you can take positive also, it's a downward direction. So W is 50,000 into, so this will be the square. Clear? 6,000 square divided by 16 into E into, sorry, value of E is 2.1 into 10 raised to 5 into value of E is I is 78.10 raised to 6. Simple. So whatever the value of slope or deflection, it will be there. So that is 0.066, or sorry, 0.068. So whether it is in degree or radian, so definitely it will be in radian. So if we want in degree, then we must multiply by 180 by pi. Simple. So theta A, or we can say theta B, it will be equal to 3.935 degree. Clear? I hope you understood the concept of the simply supported beam carrying point load, or having a eccentric load, or having uniformly distributed load, and its numerical. If you like the video, then please subscribe my channel. Thank you.